All right, lesson 3.3, compound inequalities and absolute value. So these are kind of the weird scenarios that come up that, you don't see a whole lot. You may have one section or two sections in your book in algebra dealing with some of these things. So it's kind of good to go back and refresh and kind of relearn some of the rules. So I have it kind of broken down as like a left and a right-hand side. So we'll kind of go through each side. We're going to start off with compound inequalities first. So let's just kind of go to about right here. And if you want to, you could kind of put a line right down your paper that separates these two ideas. So on the left it says a disjunction, so kind of a vocab word, is a compound statement that uses the word or. So the big picture is that it's an or statement. And when you look at the number line, you're always going to see this situation, typically, where the arrows are going to blast out in both directions. And so if I look at this solution set on here, it looks like that in red is the solutions. So it looks like as long as x is less than or equal to, because this is solid right here, less than or equal to, is that -3? Or the other part of the solution set is over here on the right-hand side, which since this is open circle, it's going to be x is just greater than +2. So you have two different types of solutions there. Numbers that are smaller than or equal to -3 or numbers that are bigger than 2. Set builder notation would basically be just writing, and I probably should have put interval notation here because I'm more concerned with that than I am set builder. Set builder, you just say, hey, it's the set of x's such that, and then you just kind of put that on there. So set builder is not a lot different from just solving the problem. But interval notation would be a little bit different because you would have -infinity, which represents here, all the way over to that -3. And that would be a hard bracket because it's equal to. And then or you'd have this soft bracket here at the 2, and then that rolls all the way out to +infinity. So interval notation would be kind of two parts, and you'd have that or in between. Now, kind of an important piece is that the disjunction is true if and only if either part is true. So you can't satisfy both pieces. There's no way you could be smaller than -3 but bigger than 2 at the same time. So as long as you make either part true, you're good to go. It's kind of like if you were to, let's say you were to roll a die and they're like, hey, you win if you get a 4 or a 6. It's not that you have to get both of them. It's just either one and you're fine. So over here on the right, a conjunction, so just a little different prefix there at the beginning. A conjunction is a compound statement that uses the word and, all right, which is quite a bit different. And typically the ands always are this intersection. They're kind of in between two different scenarios. So kind of think of it like this. So if I was going to write this out, I see that my numbers are x has got to be greater than or equal to -3, all right? And at the same time, so there's a second criteria, x has to be less than 2. So it's almost the opposite of the one on the left there. And when you have the word and in there, you can shorten it because basically you're saying that x is between 2 and -4. And it's got to be greater than or equal to -4, but less than 2. So typically we write the and statements like this instead of having two separate pieces with the word and in between. You cannot do that with the or statements. All right? There is no way to write inequality like that if you have an or situation going on. Now, set builder notation, again, let's just change this to interval. And interval notation is like, well, my left bound is -3. My right bound is 2, but that one's going to be soft. So you're trapped between, You know, the ands are kind of like the between two numbers, and the ors are kind of like you're blasting out, usually in two directions, but not always. We'll see a couple examples in the notes or homework, some special cases. Now, a conjunction is true if and only if both, well, I shouldn't even say both because it could be multiple, but all parts are true. Meaning that, like, this part had to be true and that part, they both had to be true. We're over here with the ors, it could be either one. You know, it could be this or it could be this side. If either one of those sides, you're good to go. But on the ands, it has to be both. Both have to check out. All right, let's get into actually solving some problems here. Solve, graph, and express the solution in interval notation. Set builder will be pretty much done for us. So here we go. Let's look at this one. It says x plus 3 is greater than 7, or 3x is greater than 9. So again, we're like, all right, we're thinking about ors here. Well, let's just solve them separately. On the left, I'm going to minus 3 from both sides. So I have x is greater than 4, or, well, on this one, I'm going to solve it by dividing both sides by 3, or x is greater than 3. Well, this is kind of a strange case. You know, I'll put 0 on my number line. So when I do both of these, you know, this one, I'm going to kind of write this really light. If I draw x is greater than 4, well, that's going to be basically right here. But then if I drew x is greater than 3, well, that one is right here. And all I have to do is make either one of those true. So the final answer, what you're going to put down here for your final answer, is the one that includes both of those, or what's called the union of both of those. So as long as you're in this area, you're going to make it true. You know, because I wanted to pick up like something like a 3.5. A 3.5, you know, if we just tested it and said, hey, does 3.5 work? Well, 3.5 makes this side true. It makes this side false, but it doesn't matter because all you have to do is make one part of it true. So that's why I'm going to go ahead and I'm going to do it from 3 all the way on over to include everybody. So it's kind of like the union of both pieces. So now I go to this other one, this and problem, and I divide it out. I divide by -2, divide by -2. Oh crap, we just divided by a negative, so flip your sign. And then and on this side, I add 3, and I get x is less than or equal to 5. Well, since this is an and problem, I got to be bigger than -4. So let's just kind of start drawing this out. So 1, 2, 3, -4 is chilling over here. So I'm greater than -4. So I'm heading this direction. But then at the same time, remember, both of these have to be true. At the same time, I also have to make sure that I'm less than or equal to 5. So 5 is right over here. I can be equal to, so I'm going to put it solid. So I can be greater, I got to be greater than -4, but then at the same time, I must be smaller than or equal to 5. So that's where I'm going to get kind of this in-between area, this intersection. All right? So an and problem is really like the intersection of two sets. And if you go back to like algebra or pre-algebra, the intersection of two sets, you can write it with that symbol. It's like an upside down U. The union over here is going to be written with an actual U. That means it's kind of everybody joined together. All right. Let's move on down. Absolute value. And I apologize big time, but this area right here on your notes came out of the copier really blurry. As I was working these examples out, this was really blurry, so you may have to kind of look at this slide to make it a little bit easier for you. But remember, absolute value is just basically how far you are away from 0. And the big thing that most people remember is it's always positive. You know, so for instance, if I said, hey, what's the absolute value of -8? Well, the answer is 8. And if I say, well, what's the absolute value of +8? The answer is 8. It's like whatever's in there, it's got to be positive. So on this number line, when they show the absolute value of x equals 3, there's two possibilities. It could be u or u. So always know that you're going to have two cases when solving these problems. Now, when the absolute value is less than, all right, so this one is going to be absolute value is less than. When the absolute value's got to be smaller than a number, it's going to be all the points kind of in between two numbers, and it's going to be one of those intersections, so it's going to be an and problem or an intersection problem. So that's kind of a big thing you want to remember, is that if it's less than or equal to, it's going to be an and problem. And if it's greater than or equal to, it's going to be an or problem. So like on this bottom one, if it said, you know, if I can put all the x's in here that make this true, that make absolute value of x greater than 3, well, you know, if I put the number 4 in there, if x equals 4, that would make it true. But then if I put x equals -4 in there, the absolute value of -4 is also going to be bigger than 3. So that's true. So that's why you get these two cases where they kind of blast off into both directions. And that's always going to happen with one of these OR problems. So these are going to be ORs or unions. So trying to keep those two straight, but it's a little easier when you actually solve it. So let me kind of work through the algebra, and I'm going to give you a few steps on these ones. So to solve an absolute value equation, all right, here are your steps. So steps for absolute value. So step 1 is isolate the absolute value brackets, meaning get them by themselves on one side. And you're going to have some stuff inside there. You know, I don't even care about what's inside here right now. It's just stuff. But I want to isolate the brackets. I want to get them all by themselves. Then step 2 is you need to set up and you need to solve two cases. And this is where it gets a little tricky. I'm going to kind of put a little asterisk up here. So let's start with the first example, because the equal to's, these are typically easier. And when you get down to the bottom ones, those are going to be a little bit tougher. So right now, step 1 is done. My brackets are isolated. There's nothing else on the left-hand side besides the bracket. So what you're going to do is, and just picture this. Picture you don't even know what this is. All right, picture it's just blue blob. Well, the only two things that I could put inside that box that would make this true is if this stuff in here equals 5, or if this stuff in here equals -5. And that's where my two cases come from. Because what's inside those brackets can be two numbers, I have to solve both situations. So case number 1 is, well, maybe x minus 7 turns out to be +5. And then case number 2 is like, well, maybe that x minus 7 turns out to be a -5, which would also give me +5 for an answer. So I solve both cases, and I add 7, and I add 7. I'm like, well, x equals 12. Or the other possibility is x equals 2. Both of those are correct answers. Because if I go back and I plug it in, you know, 2 take away 7 is -5, but then the absolute value of -5 is 5. And then the 12 obviously works because that just comes out to be +5. So that's where I'm solving two cases. On this next example, I first need to isolate the bracket, you know, so I got to isolate this. So what I'm going to do is I'm going to minus that 5 from both sides first. And now I have absolute value of 3x equals 9. And now I can bust into my two cases. Either 3x equals positive 9 or 3x equals negative 9 for case number 2. And then you just solve them. So this would be x equals 3 or x equals negative 3. So when you're doing your steps for solving an absolute value equation, it's pretty straightforward. Isolate the brackets, solve for both cases, one positive, one negative. All right, so maybe I'll put one positive, one negative. All right, now the toughest thing from the whole sheet will be the next couple. So we need to solve the inequality and graph the solution set. So very similar steps. So these are steps for absolute value inequalities. So step 1, isolate the brackets. All right, get that by itself. Again, who cares what's inside here, blah, blah, blah. Don't worry about it. Now, your two cases are going to be a little bit different. So your two cases, and this is just something you kind of have to memorize, is the two cases are you got to do two things. You have to flip, well, I guess I should say this. Might be easier. One of your cases is just solve as is. Don't do anything. Just solve it as it is. The second case, like on the equations, we had to do one with just what the number was. The other had to be the negative. Well, on this one, it's going to be kind of like that. You have to actually flip the sign and make it negative. All right? So you got to do two things. So hopefully this will be a little more explanatory when I do it. So let's try to rock this one out. So my brackets are isolated. Step 1 is good. So we can go right into our two cases. Well, case number 1 is just solve it as is. 2x plus 1 is greater than 5. No big deal. As is. Now, the other side, I got to do something. And this is where you might want to pay attention here. I need to flip the sign, and I got to make it negative. All right? So I did two things there. All right? I had to flip, and I had to do the opposite. All right? Those were the two changes on case number 2. Kind of hurts your brain if you try to think through why do I got to flip it? Why do I got to do the opposite? It kind of goes back to up above, but just try to memorize a rule. It's the way I've always done it. So minus 1 from both sides, you get 2x is greater than 4. So x has to be greater than 2. I knew right away that since this was a greater than problem, this should be an or problem. Should be an or situation. So I solve the other side, and I get minus 1, minus 1. So that's 2x is less than negative 6, which means x is less than negative 3. And even if you weren't sure if it was an or or an and, as soon as you start to graph it, you'll see, because x is greater than 2, well, let me just put my 0 right here. So if x is greater than 2, that would be that way. And then if I do the blue part, x is less than negative 3, you'll clearly see that this is a classic OR problem. All right? The OR problems typically take off in two directions, but they're definitely not like a barbell where you're trapped in between two numbers. They kind of fly all the way out. All right, let's try this one here on the left. I'm going to erase the steps just so I have a little bit more room. All right, so we need to isolate the bracket, which is not done yet. So I need to get rid of that divide by 2. So to get rid of this divide by 2 right here, I'm going to times that side by 2. But if I times that side by 2, I got to times this side by 2. So now I'm at isolated bracket 3x minus 9 less than or equal to 24. Sweet. Bracket is isolated. So now I got to set up my two cases. Well, case number 1, as is. Just do it just whatever's there. Case number 2, flip and change. Flip it and change it. Now, because early on this was less than, I know this is going to be an and problem, which should mean, it should be, I kind of call these like barbell problems. Like I'm going to be trapped in between two barbells. I kind of always think of it like that. You know, I think of these ors as either that scenario or you're just blasting in one direction or the other, like in the example. But you're not trapped like a barbell. All right, well, let's solve this one. So I have add 9 and add 9. That's what, 33. Divide. So I get x is less than or equal to 11. This side, when I add 9 to both sides, I get negative 15. Divide. X is greater than negative 5. So I'm bigger than a negative number, smaller than a positive number. I need to fit 11 on here and negative 5. Oh, hopefully I got enough room for this. Maybe I'll cheat way over here and slap 0 on there to the left a little bit. And let's do the two sides. So if I do less than 11, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is right here. So I'm going to be less than or equal to 11. So I'm heading this way. But then at the same time, and I also have to be greater than or equal to negative 5. So there we go. All of these numbers in here are going to make that thing true. If we test it out, it's going to make both of them true. You know, and I could pick a number in there if I'm not sure. I could try a number. I could say, well, let's try 2. Let's just see if 2 works. And I could go back up to my original equation, and I could plug 2 in. Well, 3 times 2 is 6. 6 take away 9. That's the absolute value of negative 3 divided by 2. Is that less than or equal to 12? Well, absolute value of 3 is just 3. Is 3 divided by 2 less than or equal to 12? Yeah. 1.5 is less than or equal to 12. So 2 works. I could pick a number outside that range, you know, either a number here or a number here and try it. And both of those numbers should fail. They should not work. So you can always kind of test yourself and see if you're doing this right. All right. I believe that's all we got. So hopefully that's enough to help you with the practice problems. If not, ask me in class. See you.